Hello, everyone. Welcome to today's webinar. My name is Randy. I'm from Element 14. I'll be your host today. Today's presentation from Richtek is called How to Design the Richtek RT6204 Buck Converter for Wide Input and Output Voltage Range. This webinar will be presented by Roland van Roy. Roland is the Field Application Manager for the Richtek Europe region. He has worked in consumer electronics and power electronics field in Europe and Asia for more than 25 years. At the end of the presentation, there will be a Q&A session. You can ask your questions in the Q&A window of the WebEx screen. So let me hand it over to Roland for today's presentation.
Thanks a lot, Randy. And welcome everybody to this introduction of the wide input voltage range RT6204 buck converter. In this introduction, I will explain you the following items. I will first explain you some of the advantages of the Richtek 6204 buck regulator, some of the specific details where you can use this part. I explain you some application examples, industrial, LED lighting, motor control. I will also go into detail how to design this part, which components are important to control what parameters of your application. And I will also do some actual examples of the measurement when you do these on the default RT6204 evaluation kit. Then we have a nice introduction of a special measurement technique, stability test by using the Richtek Load Transient Tool. It's an interesting alternative to standard stability testing, which uses very expensive and complicated gain phase measurements. Then I will explain you when you want to make a design and you want to find the tools, where to find the tools, how to use the tools, and also I will give you an overview of the application note, which includes formulas, calculation methods, special tricks for the application. And finally, we will have a Q&A session. In this session, I already have prepared 4 example questions, which I think will be interesting for you. And after that, you can ask your own questions. So let's go. First, let's have a look at the specifications of the RT6204 evaluation board. Here you see the board. It has an input voltage pin where you can apply input voltage in the range from 5.2 up to 60 volts, which is pretty wide range here. We also have the output voltage pins, and here you can actually set the output voltage between 0.8 and 50 volts. The maximum load range for the converter is 500 milliamps. Default, this board is set at 5 volt output, but you can make it into any voltage you want. Furthermore, we have an enable and disable header where you can do either power sequencing or just switch on or switch off the device. We have resistors for setting the output voltage. We have a capacitor which can control the soft start time if you would like to have a slower soft start to reduce inrush current. We have components, external compensation components, which are important in wide output voltage range because output capacitors and compensation need to be well tuned together. And well, this board, the RT6204, does not need an external Schottky diode because it has an internal synchronous rectifier MOSFET, which means you can save board space and BOM cost. Furthermore, this part goes automatically into PSM, power save mode, pulse skipping mode at light load conditions, which helps to improve the efficiency at light load. Then the output voltage step-down ratio can be controlled between 3.2% and 93%. Outside these ranges, you will either hit the minimum on time of the switching waveform or the minimum off time. But basically 3.2 to 93% is a very wide range that allows a lot of different step-down ratios. And finally, because this is a high voltage device, so you may want to reduce or you may want to increase your switching time to avoid EMI. So in this part, we have especially done a slew rate control on the switching waveform in order to get an EMI-friendly switching speed. Let's have a look at some examples here. So I just took some examples where this part can really be optimally used. The first example is an LED driver. I made a picture here where you can see the LED driver, you see the evaluation board, and you have an MCU control. Normally, LED drivers are using a PFC flyback converter that then generates a higher DC voltage on the secondary side for driving the LED driver. The LED driver also needs a dimming control, and this is normally done by either an MCU or maybe a Zigbee module with a wireless module on board. And this module needs 3.3 volts bias supply. And in this case, because this supply maybe is using 100 milliamps, so you cannot use an LDO to step down 50 volts down to 3.3 volts because it will become too hot. So in this case, RT6204 is a very nice solution to have an efficient step down to provide a nice low voltage supply for your MCU in an LED lighting application. Another example is a motor driver. For motor drivers, you normally need a high input voltage, like 48 volt industrial supply range, and the motor driver is normally using 2 or 3 half bridges, which each need around 15 volt biasing supply for the gate driver bias. And these normally also use in the order of 100 or 200 milliamps of driving current. So you need to use a high efficient step down from the high voltage 48 volt supply to provide this 15 volts for the gate driver section. Then you also need an MCU for the speed or position control of the motors, and this you can do via an LDO, which is stepped down from the 15 volt intermediate supply. And here again you see a very nice step down ratio, a high efficient step down ratio solution using the RT6204 in an industrial application. Another example is an iron core transformer. You know, iron core transformers don't have any regulation mechanism, so the output voltage of these transformers will fluctuate if the input voltage is also fluctuating. Furthermore, if you apply a load to iron core transformers, there will be considerable output ripple. And if you want to derive a stable supply from this kind of fluctuating input voltage, you can easily use the RT6204. One thing you have to take care of is that the input voltage minimum value is around 2.6 volts higher than the regulated value to avoid maximum duty cycle limitation. And in this case, you can see that the RT6204 can also provide nice stable supplies from highly fluctuating input supplies. Let's have a look at some of the design considerations for RT6204 application. Here you see the general application circuit, and I will discuss each component parameter, how it affects the application. First of all, you have the feedback network, which is used to set the output voltage. The impedance of this network is not important, just the R2-R1 ratio, which will set the output voltage via the 0.8 volt reference. The output capacitor is normally selected to choose a certain output ripple or to give a certain load transient behavior, for example, a certain percentage of sag when you do a fast load transient. We have the inductor, and the inductor normally is chosen to provide a 30% current ripple, which is around 150 milliamps, and sometimes the current slope of the inductor needs to be considered in high duty cycle applications. The application note will give you more details how you can calculate this. The compensation network is important to set the control bandwidth of your converter in combination with the output capacitor and the output voltage. So any specific output voltage, output capacitor combination will require a certain component of choice in the compensation network. Again, the application note will give you all the formulas, but you could also use the design tool to calculate this for you. We have a soft start capacitor, which is setting the soft start time. Especially when you have higher output voltages or big output capacitors, you will want to choose a slow soft start time to avoid inrush current at the input. We have an enable pin which either can be connected directly to the input voltage or it can be connected to a resistor divider to set a certain input voltage dependent startup behavior. And finally, the input capacitor is normally chosen to choose a certain amount of ripple on the input voltage rail. Too much ripple on the input voltage rail can pollute your system and also causes EMI. Another thing to consider is the RMS current in this capacitor. When you are having high duty cycle applications that can exceed 65%, we normally recommend to add an external biasing circuit to charge the bootstrap capacitor. In high duty cycle applications, the bootstrap capacitor may not be sufficiently charged due to very short on-off time, and then the external bootstrap capacitor can guarantee sufficient charging under all duty cycle conditions. Finally, EMI can be reduced further by adding a snubber to the switching waveform. But normally, you will not need this in most applications because the RT6204 has an EMI-friendly footprint. Let's have a look at the actual 5-volt default output of the evaluation kit and see what kind of components we chose to get the certain performance. First of all, we set the output voltage with the resistors for 4.98 volts, so around 5 volts. We have selected the output capacitors for around 26 millivolts ripple in the pulse skipping mode, but when you go to the PWM mode, so the continuous conduction mode, this ripple will become much smaller, only 5 millivolts. We have selected the inductor value for about 130 milliamp current ripple, which is around 26%. And this is a nice target value for any application. The compensation network has been set for a control bandwidth around 32 kilohertz, and a phase margin will be around 50 degrees, which is a nice stable behavior. The soft start capacitor in this case has been selected to have a soft start time of around 18 milliseconds, which normally will not give you any inrush with any output capacitor for 5-volt applications. You can see that the enable pin has 2 resistors. They are currently selected to have an immediate startup when the input voltage rises above 3 volts, or basically above the UVLO point of the input voltage. But by changing the R5-R9 ratio, you can make the converter start up at a certain input voltage. For example, if you would like to start up at 10 volts, then you have to set the divider in such a way that the enable threshold of 1.25 volt is reached when the input voltage reaches 10 volts. The output capacitors here are selected for about 30 millivolt peak ripple on the input voltage rail. So these are the design targets of this evaluation kit. Let's have a look at the actual measurements of this evaluation kit. Here I look at the output ripple measurements, where I apply the voltage probe of my oscilloscope with very short leads on the output capacitor, and the short leads are needed to avoid any inductor stray field pickup that could cause an influence in my measurement. Another thing to consider is that the output voltage ripple actually depends on the load condition of this converter. If you operate in light load, you will see pulse skip mode behavior, and this will give you a higher output voltage ripple. Here at 10 milliamps load, the operation mode is PSM. You can see that the switching frequency is much lower than the nominal switching frequency, only 23 kilohertz. The output ripple in this case is around 28 millivolt peak. When you go to higher load conditions, you will see that the frequency gradually increases, but still operates in PSM mode at 100 milliamps. And you see that the output ripple basically stays around constant because in PSM mode, this converter works in a hysteretic control mode, which is actually regulating the output voltage ripple. When you finally go to high load condition, now you see that the converter operates at 350 kilohertz, which is the nominal switching frequency for continuous conduction mode. And the output ripple now is much smaller. If you don't regard the noise pickup, you will see the output voltage will be around 5 millivolts, but including the spikes due to the noise pickup, the scope measures around 14 millivolts peak. So this is the load ripple based on different load conditions. Let's have a look at the enable pin. Now I start to look at, I will add an enable switch to the enable header, and you will see when you switch on the converter, the output voltage rises very gradually down to the final value of 5 volts. You can also see that the soft start time here is around 19 milliseconds, which is pretty close to our calculated value. And you can see that this is the converter switching frequency. In order to achieve this very nice, smooth startup, we actually gradually increase the switching frequency in order to make these very short duty cycles during the switch on time. If you want to use the resistor divider on the enable pin to make a startup condition at different input voltage, you can choose this resistor divider, and the only thing that you have to take care of is that the threshold of the IC at enable is around 1.25 volts. So when you set the resistor divider for an input voltage where you reach the 1.25 volts, the converter switches on. Please note that the RT6204 enable pin has a high voltage rating. So you don't have to worry about exceeding a certain voltage with the enable pin, because it can basically be connected directly to the input voltage without any risk of damage. High duty cycle applications normally require an external charging bias voltage for the bootstrap capacitor. And when your application can exceed 65%, we recommend to add this circuit, and normally this circuit can be biased from the output voltage supply. You need around 3.3 to 4 volts bias voltage with a small buffer capacitor, and in this case I made it with a small resistor and a Zener diode and an extra capacitor with a standard diode to charge the boot capacitor. I will show you what happens if you don't use this circuit and you have high duty cycle application. Here you see an application where the input voltage is 6 volts and the output voltage is 5 volts. So this is really a high duty cycle application, but I did not add this bootstrap circuit, charging circuit. The switching waveform will show a regularly very longer period of low side MOSFET on time. And this is basically caused by the fact that the bootstrap capacitor, due to these very short off times, is not able to charge by the internal charging network, and this causes at certain point a too low voltage on the bootstrap capacitor. In this case, the IC under voltage protection will force the low side MOSFET to be on for a longer period to recharge the boot capacitor. But this causes irregular switching, and the result is a higher ripple voltage on the output. To avoid this, you can add this circuit, and now there is sufficient current to charge the bootstrap capacitor even in very high duty cycle application. The switching is very regular, and there is no more under voltage protection, and the output voltage ripple is extremely small. So for any, I have here a small circuit. You can see it's a very simple circuit to add between the output voltage, ground, and the bootstrap pin. So for high duty cycle applications, it is highly recommended to add this little circuit. Let's have a look at higher output voltage applications. Because RT6204 can be used with output voltages up to 50 volts, the output capacitor is something to consider. In low voltage supplies, you normally use MLCC ceramic output capacitors. But you have to consider one thing. MLCC output capacitors have a DC bias effect. It means that when the DC bias across the capacitor increases, the rated capacitance drops from the original 10 microfarad value, and it drops considerable at 12 volt. In this case, it drops almost 70%. So when you would design a 12 volt supply with a 10 microfarad ceramic capacitor, the actual capacitor at 10 volt DC is only around 3 microfarads. And this can cause stability and other problems like higher ripple. So for high output voltage supplies, it is better to use electrolytic output capacitors, because these capacitors don't have a DC bias effect. One thing to consider is that in case you use an electrolytic capacitor, electrolytic capacitors have considerable ESR. And also this ESR is temperature dependent. So when you design with electrolytic output capacitors, you have to consider the temperature behavior of the ESR. And in this case, we will set the converter control loop to be much lower than what we would do when we are using ceramic output capacitors. So we will choose the control loop to be around 12 kilohertz. The compensation network definitely needs to be calculated to fit the output capacitor type. You can use the application note to see how this is done, but you can also use Richtek Designer automatic design tool, which will select for you the automatic the most ideal output capacitor for the chosen output voltage, and then it will automatically calculate for you all the compensation values for a stable design. Let's have a look at the stability of this converter. Normally, converters are tested on stability by using a gain phase analyzer, but this is an expensive equipment and also quite complicated. The measurement is not so easy to do. Here is an alternative method to test converter stability. I apply a fast load step to the output, and the load step needs to be really fast. Normal electronic loads are normally not fast enough to do this. So I use an external circuit which has a MOSFET switch, a dynamic load resistor, and a static load resistor. The static load resistor is needed to put the converter into continuous conduction mode. You can only measure stability in continuous conduction mode. You should not use PSM mode for stability measurements. So what happens is you get this very fast pulse load. And by looking at the pulse load shape, which is shown below here, you see the output current and the output voltage during the load step. The shape of the output voltage will tell you whether the converter is stable or not. This very smooth, nice response is a very stable design with a phase margin around 58 degrees. If you go to slightly worse phase margin, you will notice that the output voltage step load response will show some bump. This picture still is acceptable. It will have a phase margin around 45 degrees. When you go into worse stability, you will notice that the bump becomes more distinguished, more clear. There will be maybe an extra bump on the second time, and this indicates that the stability of your converter becomes marginal, in this case around 41 degrees. And when you see this kind of waveform with a lot of ringing in the step load response, you know you have a problem. The phase margin will not be sufficient and you have to make some modifications to your application. To make a simple load check, Richtek has developed the Load Transient Tool, which is available at Farnell and E14. And this Load Transient Tool includes all the components in order to do a very quick load transient test. It has an onboard pulse generator, which is MCU based, so it's very stable. It has a MOSFET switch. It has 7 selectable pulse load resistors, so you can choose with a jumper which resistor you want to use in order to set a certain pulse load amplitude. You have connections for the static load connector, and we apply also in this tool a adjustable static load resistor. And here are the alligator clips for connecting it to your application. There is underneath the board a battery pack, so this tool is completely portable and completely isolated, which means you can use it at any part of your application without having issues like ground loops or other problems. 3 buttons on this board will control the frequency and the duty cycle over a very wide range. So this board can be used to test almost any converter, from buck converters to boost converters to linear regulators. You can even measure LED drivers with this tool. The total tool kit, it will include batteries, the load transient board, and an adjustable power resistor. And it also has extensive documentation to teach you how to use this tool to test various converter types and what you need to take care of when you use this tool. I will now show you an example on the RT6204 evaluation board in combination with the Richtek Load Transient Tool. Here you can see the connection, and there is a couple of things that you have to take care of. When you do the load transient test for stability check, you have to apply about 33% static load and 33% dynamic load. And this percentage is the percentage of the maximum rated IC current. This means that if you operate in this method, you will ensure that you will not run into PSM mode, which could make the result of the measurement invalid. So I apply a static load resistor. In this case, I didn't use the load resistor with the board because the resistance wasn't high enough. So in this case, I use an external 27 ohm static load resistor, which gives you around 37% load on the static side. And I use the jumper to select the 22 ohm dynamic load, which gives you around 45%, which is still okay. Then I measure the load current and I measure the output voltage directly on the output capacitors of the converter. Let's have a look at the results. This is the result of the fast load transient on the RT6204 evaluation board. You see that the result is very nice and smooth. There is no big bumps or dips or ringing. This means that it is a very stable design. But you can learn a bit more from this measurement. Because this is a very fast load step, you can zoom in to the actual response time of the converter. This is the time it takes from the converter initial load step to the time where the converter starts to put the output voltage back to the original value. This is called the response time. And here I measure around 7.8 microseconds. This response time can be used to calculate or estimate the control bandwidth or the unity gain frequency of your converter. And in this case, I get 0.3 divided by 7.8 microseconds is about 38 kilohertz. And you have to know for current mode regulators, we normally set the control bandwidth to be 1/10 of the nominal switching frequency. Since the RT6204 is operating at 350 kilohertz, the bandwidth should thus be around 35 kilohertz. So 38 kilohertz measurements is pretty close to what you would expect. And this just gives you an indication that your design is probably okay. Let's just compare this with an actual gain phase measurement, which I did with the same application as I did for the fast load transient. I used an expensive, complicated measurement, and I measured the gain and the phase in the same condition. And you see that the bandwidth in this case, which is at this point, is around 33 kilohertz, and the phase margin is around 51 degrees. So you see that with the fast load transient tool, the results you get are pretty close to the actual gain phase measurement. But it is much easier and much less time consuming. So using a Richtek Load Transient Tool can quickly help you to identify whether your converter is stable or not. Here I design, if you start to use the RT6204, you probably want to use a tool for quickly designing this part. Richtek has the Richtek Designer online simulation tool. When you go to the Richtek website, you will find this banner on the front page of our website. Select Richtek Designer, and you can key in already your application values. In this case, I chose 50 volt input, 15 volt output, and 0.5 amps output current. I click Design, and then the tool will tell you which parts are suitable for this application range. And here you can now select the RT6204, which meets these criteria. When you press Select, automatically the tool generates for you a full circuit based on the input conditions that you provided. So 50 volt input, 15 volts output, and all the components have been already calculated to get you a stable design. Like I mentioned, for 15 volts, we normally recommend electrolytic output capacitors. So here the tool already selected electrolytic output capacitor of 47 microfarads, and the compensation has been calculated to fit this capacitor. The inductor has been selected to have the right value. Soft start has been selected to avoid inrush. So basically, this design is ready to be implemented in any application. You can, of course, make changes to these components if you would like to use slightly different values. But you can also directly run various simulations that you see on the top here. Let's have a look what you can do. First of all, you can do steady state analysis, and this gives you the switching waveforms. You can go into detail in the output ripple. You can look at all the currents and voltages in the different components and your application. You can also do a load transient. When you set a certain load transient at the output load, you will see exactly the same results as what you would do when you use the Load Transient Tool. And you can also use this to see the effect and the shape of the waveform when you do a fast load transient. You can also do startup analysis. You will see the startup current in the inductor. You will see the output voltage rising. You can do timing measurements. And you can also do the gain phase analysis. So basically you could see the relation between the transient analysis and the gain phase analysis. And when you make changes to your components, you can rerun the analysis to see if your phase margin is good or not. Finally, we also provide efficiency and power loss analysis, so you can check whether the IC has any heat problems or if you can meet your efficiency target. And you can see here that at a certain moment the IC goes into pulse skipping mode. So when you have a light load condition, here you see the bump where the IC goes from CCM mode to PSM mode. So you see that the efficiency slightly increases. Finally, we will have a complete bill of material generation, and we have taken care that all the components in this bill of material will result in a stable design. So we have taken some care that the component derating effects will not immediately lead to instability problems, but for sure you of course have to check with your own components whether these components are indeed suitable based on DC bias effects, ESR effects, etc. We have also an application note, AN049, which gives you a full overview of various calculation methods. You can find this on the Richtek website by choosing RT6204, go to the product page and then select documents. In the documents you see the reference designs, but also the application note for this converter. I provide in this application note all the formulas for calculating the components, like the compensation components, but also the inductor. I will also go into detail on protection features. So when you do a short circuit protection, how does the IC work? What will be the currents in the components? And finally, we will discuss 4 different application examples from 1.2 volts, 5 volts, 12 volts, and 24 volt output, with all the calculations of the components and also the measurement results for each application. So I think we have covered basically all the topics of the presentation. I will now go to the question and answer section, where I will first give you 4 different questions, which probably are something that you might have wondered of yourself. So the first question here: which components are most important for converter stability? I often have questions from customers for this. And in current mode converters, you have to realize that stability problems are normally related to the choice of the output capacitor and the compensation network, whether they match or not. As I mentioned, most problems happen when you use the MLCC ceramic output capacitors, but you don't take care of the MLCC bias effect. And it means that when you choose a 10 microfarad capacitor, the actual capacitance in your circuit may not be 10 microfarad at all. And this results in a different converter bandwidth, and it also means that the compensation network, when you calculate it for 10 microfarads, will not be correct because the actual capacitance is not 10 microfarads. Let's see the example here. Here you see the output capacitor, here you see the compensation network. A very simple rule. When your output capacitor was designed for example, 20 microfarads, and your compensation network was also designed for 20 microfarads, but the actual output capacitor due to the MLCC DC bias effect is only 10 microfarads, you have to reduce the compensation resistor in the same ratio as the output capacitor drop. So when it was for 20 microfarad design, you would choose 24K compensation resistor, but actual capacitance is only 10 microfarad. the compensation resistor needs to be reduced to 12K in the same ratio as the output capacitance. In this case, the bandwidth that was increased by this lower output capacitance will be reduced by the lower value of the compensation and will become back to the original 35 kilohertz range. And of course, you can use Richtek Designer to check this and to see the effect of output capacitor and the compensation resistor on the AC analysis gain and phase results. Another question, in which application is RT6204 most suitable? Well, since this is a wide input and wide output voltage range converter, basically you can use this IC as a very nice building block in almost any application, and especially applications where you have either a very high input voltage range or a very fluctuating input voltage, or you need a very high output voltage. For example, automotive applications where the car battery can go from very low voltage when you start the car battery, when you start the engine, or go into peaks when you have load dump effects, you can use RT6204 without any damage, because this IC can withstand very high voltages up to 80 volts. Solar arrays are another example. A solar array produces a voltage which is dependent on the daylight condition. So if you put solar arrays in series, but there is a cloud in front of the sun, the voltage drops and you would still like to provide a stable output voltage from a fluctuating input voltage. Here, RT6204 is really suitable. If you have an application that runs from a 12 volt input lab supply to make a 5 volt output, of course you can use 6204, but we have many other ICs that may be more suitable. For example, the Richtek ACOT, the Advanced Constant On-Time parts, which have a very good transient performance, may be more suitable because these parts are 18 volt rated, which is really suitable for 12 volt inputs. And then I wouldn't use the RT6204. Another question, when do you use an LDO for step down and when do you use RT6204? Basically the choice whether you use an LDO or not depends on the LDO power dissipation. The power dissipation of a linear regulator equals the voltage drop across the regulator times the load current. So if you do this calculation, V in minus V out times I load for your application, and you find that the power dissipation will become more than 1 watt, it is probably better to use a switching regulator like the RT6204. Some examples. 48 volt input, I want to make a 3.3 volt 10 milliamp standby supply. Well, you do the calculation, 48 minus 3.3 times 10 milliamps is around 0.45 watts, which is pretty good for any LDO. So you could use RT906833 fixed LDO with a 60 volt input rating and 50 milliamps current rating. This LDO has a dissipation maximum around 0.8 watts, so 0.45 watt is not a problem. But if you would like to make a 15 volt 100 milliamp supply from 48 volts, here you will find 3.3 watts dissipation. You must use RT6204. Final question, can you make a negative supply from a positive input supply using RT6204? And yes, this is possible. It's a bit less regular, but you can use this IC in what we call the inverting buck boost configuration. Below example here is an input voltage from 5 to 48 volts and an output voltage of 12 volts negative. It looks like a buck converter circuit, but the difference is here. You connect the output not to the output, but actually to ground. And now the IC input, the IC ground rail and all the other components that are referenced to this IC ground are actually becoming the negative rail. And now this circuit works into inverting buck boost. And this has a slightly different duty cycle behavior. The duty cycle is V out over V in plus V out, which is different from buck. And also the inductor peak current is also duty cycle dependent, which is different from a buck converter. So you will find from these formulas that the maximum load current of this application is lower than a buck converter. Basically what you have to take care of when you use the IC in this range is that the total voltage between the V-in pin of the IC and the ground pin of the IC is the input voltage plus the negative output voltage, which is higher. So totally, the maximum input voltage that you can reach with this application is 60 volt, the rated IC voltage, minus the output voltage is, in this case, 48 volts. The output current is discontinuous. In the output capacitor, the current is discontinuous. And this is giving you some slightly higher ripple when you compare it to a buck converter. In this case, it is recommended to use MLCC output capacitors for lower output ripple. But basically, for calculating all the components like the inductor and the compensation, you can just use the standard buck design. So you design the buck converter for 12 volt output, you get all the components for the 12 volt output, and you just make these different application connections, and you have a negative voltage supply. Here's the example. I did this on my little, what I call a copper board. So I just did a single-sided little layout for this IC in this application. And you see with 24 volt input, 250 milliamps output load current, the output ripple is actually quite okay at 36 millivolts. And the output peak, the inductor peak current at 250 milliamp load is around 460 milliamps. So you see that this application is not able to deliver the full load current of the IC rated load. Actually, this application can only reach around 380 milliamps maximum load condition. And this output load is input voltage dependent. So I hope this was interesting for you. I think we are at the end of the total session. If you have any question, now is the time to ask. So if you have a question, you can put your question in the chat box, and I will see it, and I will answer any questions you have. Now, basically, RT6204 is really a nice building block. It's extremely flexible. So any application that has a load current requirement which is less than 500 milliamps, basically this IC can be used. And I would think that I use it myself in some hobby projects, motor control, LED lighting. It's a really versatile part and very easy to use because we have automatic design tools. So you don't really have to understand all the details of this converter. And with the application note, you should have no trouble in finding the solution to your application requirement. Well, it seems there are no questions, so I guess that means that my explanation was very clear. I hope so. And well, in that case, if there is really no other questions, then I wish you all a very good day. And if you, of course, have any questions on this IC, you can always go to Richtek support, put a question there, and we will take care of it, that we will help you in finalizing your application or to answer any specific questions you have, whether it's on this IC or whether it's on any other Richtek part, or maybe even some special external component related questions on MLCC capacitors or on electrolytic capacitors. We're always well willing to help you in any technical power management problem you may have.
That concludes today's webinar. I'd like to thank Roland for giving a truly informative and excellent presentation. And I'd like to thank everyone who has attended. Take care.
Thank you, Randy. Goodbye, everybody.